Welcome to the video on Computer Vision, Unit 4 3D Reconstruction. It's the first part of the video. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. Many stereo matching techniques have been developed to reconstruct high-quality 3D models from two or more images. Stereo is one of the potential cues that can be used to infer shape from the images. A number of such techniques, which include not only visual cues such as shading and focus, but also techniques for merging multiple range or depth images into 3D models, as well as techniques for reconstructing special models such as heads, bodies, or architecture are available. Shape from X. In addition to binoculars disparity, shading, texture, and focus all play a role in how we perceive a particular shape. The study of how the shape can be inferred from such cues is sometimes called shape from X, because the individual instances are called shape from shading, shape from texture, shape from focus. So the X may be either shading or texture or from focus. So any of the characteristics of the object, we are recreating the shape. So the three cues and how they can be used to reconstruct the 3D geometry is called as the shape from X, and they are shape from shading and photometric stereo, shape from texture, and the third one is shape from focus. Among the various cues that can be used to infer shape, the shading on a surface can provide a lot of information about local surface orientations and hence overall surface shape. This approach becomes even more powerful when lights shining from different directions can be turned on and off separately, which is called as photometric stereo. Texture gradients, that is the foreshortening of regular patterns as the surface slants or bends away from the camera, and they can provide similar cues on local surface orientation. Focus is another powerful cue to scene depth, especially when two or more images with different focus settings are used. Shape from shading and photometric stereo. When you look at images of smooth shaded objects, such as in this figure 13.2, you can clearly see the shape of the object just from the shading variation. It is possible because the surface normal changes across the object and the apparent brightness changes as a function of the angle between the local surface orientation and the incident illumination. The problem of recovering the shape of a surface from this intensity variation is known as shape from shading. This diagram shows the synthetic shape from shading. So from in these two, the light is in front, and this C and D, the light is front right, and corresponding shape from shading reconstructions using the technique of this method. Shape from shading. Most shape from shading algorithms assume that the surface under consideration is of a uniform albedo and reflectance, and that the light source directions are either known or can be calibrated by the use of a reference object. Under the assumptions of distant light sources and observer, the variation in intensity, this is called as the irradiance equation, which becomes purely a function of the local surface orientation. I of x comma y will be equal to r of p of x comma y comma q of x comma y, where the p comma q, which is equal to zx comma zy, are the depth map derivatives, and r of p comma q, which is the reflectance map. For example, a diffuse surface, which is also called as a Lambert surface, it has a reflectance map that is non-negative dot product between the surface normal. So surface normal n cap p comma q comma 1 divided by 1 square root of 1 plus p square plus q square, and the light source direction is given by v. Then the reflectance is this given in this equation, where rho is the surface reflectance factor, which is also called as the albedo. In principle, equations of I and R can be used to estimate this p comma q using non-linear least squares or some other method. Unfortunately, unless additional constraints are imposed, there are more unknowns for each pixel p comma q than there are measurements I. One commonly used constraint is the smoothness constraint epsilon s, and the equation is given. The other is the integrability constraint, that is epsilon I. So smoothness represented by the s, so constraint is epsilon, so epsilon s, and integrability constraint it is epsilon I, which arises naturally because for a valid depth map z of x comma y with p comma q will be equal to zx comma zy, where px is equal to zxy, which is equal to zyx, which is equal to qx. So instead of first recovering the orientation fields p and q and integrating them to obtain a surface, it is also possible to directly minimize the discrepancy in the image forming equation I, while finding the optimal depth map z of x comma y. Shape from shading is susceptible to local minima in the search space, and like other variational problems that involve the simultaneous estimation of many variables, can also suffer from slow convergence. Shape from shading. In practice, surfaces other than the plaster cast are rarely of a single uniform albedo. Shape from shading therefore needs to be combined with some other technique or extended in some way to make it useful. One way to do this is to combine it with stereo matching or known texture surface patterns. The stereo and texture components provide information in textured regions, while shape from shading helps fill in the information across uniformly colored regions and also provides finer information about the surface shape. Shape from shading and photometric stereo. Lambosian surface. Light falling on it is scattered such that the apparent brightness of the surface to an observer is same regardless of the observer angle. So in whatever angle you are viewing those surface, it appears to be having uniform brightness all over the surface. So such a surface is called as the Lambosian surface. Perfect reflecting diffuser. A perfect reflecting diffuser, PRD, it's a theoretical perfectly white surface with Lambosian distance, that is the brightness will be same in any point of view. It does not absorb light, giving back 100% of the light it receives. So whatever it receives, it is reflecting 100% in the surface. That is called as a perfect diffuser. That is the perfect reflecting diffuser, PRD. Another way to make shape from shading more reliable is to use multiple light sources, and selectively you can turn it and turn off, so that this combination technique is called as photometric stereo. As the light sources play a role analogous to the cameras located at different locations in traditional stereo. So for each light source, we have a different reflectance map, R1 of p comma q and R2 of p comma q, given the corresponding intensities I1, I2, etc. at a pixel. We can recover both an unknown albedo rho and a surface orientation estimate p comma q. For diffused surfaces, if we parameterize the local orientation by n cap, then we get for non-shadowed pixels is a set of linear equation. The equation form is ik, which is equal to rho n cap dot vk, where your rho n cap, it is using linear least squares, and the equation is well conditioned since we are having many number of vectors vk which are linearly independent. That is, they are not along the same azimuth angle. That is the direction which is away from the viewer. So the diagram, it shows the multi-view photometric stereo. Reflectance map, so it will relate the image irradiance I of x comma y to the surface orientation p comma q for a given source and the surface reflectance. So Lambertian case means the K denotes the source brightness and rho denotes the surface albedo, that is the reflectance, and C denotes the constant in the optical system. So this is the equation of the image irradiance. So I equals rho by pi kc cos theta I, rho by pi kc n dot s. So n dot s is the vector, your n and s surface vector. So this is the final equation for the image irradiance. Next is the photometric stereo. Again for Lambertian case, this is the equation for your I, and the image irradiance is denoting the vectors n and s1. So I1 equals rho into n dot s1, and I2 will be equal to rho into rho n dot s2. So this is for the second surface. So this will be the equation. So generally Lambertian equation, this is denoted by I. So for each surface you are going, that is a light which falls over and get reflects, and you are capturing it over the camera. So the first I1 is these two vectors. So rho n dot s1. Then light at this position is on, switched on. Then I2, it gives, that is your light position is here, and when this light is switched on, again you capture an image. So I2 will be equal to rho into n dot s2. So in this angle. And I3, this is the position of the light, third position, and again you capture a message, capture an image. So I3 will be equal to rho into n dot s3. And so cumulatively you write it in the matrix form I1, I2, I3 equals rho into S1 transpose, S2 transpose, S3 transpose into n vector. The next technique is shape from texture. The variation in foreshortening observed in regular textures can also provide useful information about local surface orientation. And the figure, it shows an example of such a pattern along with the estimated local surface orientation. So this is the diagram, which is the synthetic shape from texture. So a regular texture wrapped onto a curved surface and corresponding normal estimates, and this is the shape from different mirror reflections, and a regular pattern reflecting off a curved mirror. So you have a curved mirror surface. This is the actual picture you have, but when you view it, you can see how it is different. All the straight lines have now turned to curved lines. Similarly, your D, the curved lines from which the 3D point locations and normals can be inferred. So everything is different in that. So the shape from texture algorithms, it require a number of processing steps, including the extraction of repeated patterns or the measurement of local frequencies to compute the local affine deformations, and a subsequent stage to infer local surface orientation. A generative model is used to represent the repetitive appearance of textures and jointly optimizes the model along with the local surface orientations at every pixel. When the original pattern is regular, it is possible to fit a regular but slightly deformed grid to the image and use this grid for a variety of image replacement or analysis tasks. This process becomes even easier if specially printed textured cloth patterns are used. The deformations induced in a regular pattern when it is viewed in the reflection of a curved mirror. So it can be used to recover the shape of the surface. It is also possible to infer the local shape information from the specular flow, that is the motion of specularities when viewed from a moving camera. Next is shape from focus. A strong cue for object depth is the amount of blur which increases as the object surface moves away from the camera's focusing distance. Moving the object surface away from the focus plane increases the circle of confusion according to a formula that is easy to establish using similar images. To estimate depth from the amount of defocus, practically a number of issues has to be addressed. First one is the amount of blur increases in both the direction as you move away from the focus plane. Therefore, it is necessary to use two or more images captured with different focus distance settings. The second issue is the magnification of the object can vary as the focus distance is changed or the object is moved. This can be modeled either explicitly or using telecentric optics, which approximate an orthographic camera and require an aperture in front of the lens. The amount of defocus it must be reliably estimated. A simple approach is to average the squared gradient in a region, but this suffers from several problems, including the image magnification problem. So a better solution is to use carefully designed rational filters. So this picture, it shows the real-time depth from defocus. Thank you. With the end of the part 1 for unit 4 in computer vision.